Welcome back to Transformer series. In video 1 we covered why the old recurrent model hit a wall. In video 2 we saw how attention was invented as an add-on to fix the compression bottleneck. Today we'll take a final step. Not a step but a leap actually. We are going to see what happens when you take that attention idea and make it the entire architecture. No recurrence, no convolution, nothing else, just attention. In the last video we left off with a lingering problem. Attention has fixed the quality issue. The decoder could now look back at the whole source sentence at every step. But the encoder and decoder were still recurrent. They still processed token one at a time in order, like a worker on an assembly line. And the sequential bottleneck limited how fast we could train. So here's the question that launched the transformer. What if we get rid of the assembly line entirely and let every worker see every other worker at the same time? Here's what we'll cover today. First, our core proposal. Attention as the only computation, nothing else. Second, full encoder-decoder architecture built from attention block. Third, why you need positional encoding when there is no recurrence. And fourth, the core attention equation, how it routes information between these tokens. Every great architecture shift can be distilled into a single core proposal. And here is it in one sentence. Use attention as the central computation, remove recurrence and convolution entirely. That is transformer. So what exactly got removed? Recurrence. First we remove recurrence. No more processing token one by one. No more sequential dependency that blocked parallelism. Convolution. No more fixed window local patterns. The model see all positions at once. Okay. Then what we kept? We kept attention. The same mechanism we learned in the last video, that is computing relevance score and building weighted context vectors. But now it is not an add-on to recurrence, it is the architecture. And this shift made the model dramatically more parallelizable during training while matching or exceeding the quality of the best recurrent models that were available. Training got faster, results got better, and the field changed overnight. The best mental model for understanding this shift is a change in how words communicate with each other. On the left, the old way, a conveyor belt. Word passed through one step, one by one. Words pass through one by one. Word 5 cannot be processed until word 4 is done. You can see the animation here. Each word waits its turn, and the active word is while the active word is being processed. On the right, the new way, a discussion table. Every word sits at a round table and can see other word simultaneously. Look at the connections between them. They all are active at the same time. There is no waiting, everything happens in parallel. And this is the fundamental shift. The transformer does not march through time. It computes all relationship in one parallel step. This is what makes it so fast to train on modern GPUs. Instead of processing one position at a time, you process every position at once. Now, the original transformer still uses an encoder and decoder structure. It was actually designed for translation, right? After all. But both sides are built entirely from attention-based blocks. Here's the full picture. On the left, you have encoder stack. 6 identical layers are stacked on top of each other. This whole is one stack. They are stacked on each other. Each layer has two main sublayers, self attention and then a feed forward network with residual connection and add and normalize layer around each one of them. On the right, you have the decoder stack, also a 6 layer, but with an extra sublayer. The decoder has a mask self attention, then encoder decoder attention, which is where decoder look at what encoder produced, and then a feed forward network. Both stack repeat the same layers, these all layers, 6 times. This is deep stacking and it is important. Early layer captures simple patterns and deep layer build up more abstract long range relationship. Each layer refines what the previous layer produced. Let us zoom into one of those encoder layer and understand each piece what they are actually doing. Here is the data flow, reading from bottom to top. First is the multi-head self-attention. Every tokens look at every other token in the input and computes relevant score. This is how model build contextual understanding. That is the word bank learns whether it means a river bank right now or a financial bank by attending this to the surrounding words that are there. Right? Second, add and layer normalize. A residual connection adds the sublayer's input back into its output. So the information is never lost. Then layer normalize keep values in a stable range. This appears after every sublayer. It is the glue that keeps the deep stack from falling apart. Third is the position-wise feed forward network. After attention fixes the information between tokens, this step processes each token and update representation through a small neural network. It is applied independently to each position. Same network, same weights, but each token gets processed on its own. Here is how I think about it. Each encoder layer is like a round of discussion at a conference. So in this particular case, we know 6 deep layers, right? So 6 times the discussion happens. First, every participant listens to every other participant and take notes. That is self-attention. Then each participant goes back at their desk and reflects individually on what they heard. That is feed-forward network. And the residual connection, that is like keeping your original notes and adding a new insight on top, rather than rewriting everything from scratch. The decoder has an extra sublayer compared to the encoder, and one critical modification. The first sublayer is the mask self-attention. Same as encoder self-attention, but with a critical mask. Each position can only attend to earlier position. So when generating word 4, the model cannot pick at words at 5 or 6 or 7 location. This preserves the auto-regressive property. The prediction must flow from left to right. The second sublayer is encoder-decoder attention. This is where decoder look at the encoder output. The queries come from the decoder, but the keys and values come from the encoder. We'll look at what is key, value and query in a short while. This is the same cross attention mechanism we learned in video 2, now integrated as a sublayer in transformer. The third sublayer is the same feeds forward network as the encoder. Process each position independently. Okay, the mask in the decoder's self-attention is not optional. It is what makes the model useful for generation. Look at this example. We are generating the sentence "the cat sat on the" and trying to predict the next word. On the left, without a mask, the model can see Matt while trying to predict Matt. That is cheating. It copies the answer and instead of learning to predict, right? And at test time, the future word do not exist, right? So a model trained this way would be pretty much useless. On the right, with the mask, future positions are blocked. The model must genuinely predict Matt using only the word that came before it, right? Training matches inference, which is what we need. And here is the clever part. The mask set failure attention score to negative infinity before softmax. So softmax of a negative infinity is what? It will be 0. So those positions become completely invincible. Sorry, not invincible, invisible. This lets you still train on the full sequence in parallel. Process all positions at once, right? That's the key thing. We want to process all position at once, while each positions only see the past. Best of both worlds. Now, removing recurrence solved the parallelism problem, but it created a new one that seems almost embarrassingly simple. In an RNN, the position is built in. The model processes word 1 first and then word 2 and then word 3. The order is backed into the computation. But in the self-attention treats its input as a set, not a sequence. It computes all pairwise relationship at once, right? And nothing in that mat tells the model which word come first. Look at these two sentences. The dog chased the cat chased the dog. Same words, same set of words, same set, but completely different meaning. Without positional information, the model literally cannot tell them apart. You can try it yourself. Let's click scramble word. Here it says that the dog chased the cat, and let's scramble it. Right? The sentence falls apart. The words are the same, but the meaning is gone. And let's now click restore order to see how much the position matters. Since the architecture has no concept of no concept of order, we must inject positional information directly into the input representation. Each token gets a unique positional signature added to the embedding before anything else happens. The original transformer used a sinusoidal function for this. Let me show you how that looks like. The original transformer used a clever mathematical trick, sine and cosine waves of different frequencies to give each position a unique fingerprint. On the screen, you can see a positional encoding visualized. Each color line represent one dimension of the positional encoding. Low frequency waves, the one that change slowly, like this one, capture the broad position. Is this the beginning of the sentence or the end of the sentence, etc. The high frequency waves, the one that change fast, capture the fine-grained positions. Is the token right next to the previous one, for example? We can use slider to increase the number of dimension it shows, and also you can reduce the dimensions, right? See how the pattern is building up? With each dimension, every position gets completely unique combinations of values, a unique fingerprint. But why sinusoid specifically? Because the encoding of position p plus k can be expressed as a linear function of encoding at position p. That means the model can learn to attend to relative position, 3 word ahead, right? 3 words ahead or 2 words behind as a simple pattern, not just an absolute position. It is a remarkably elegant solution. Now let us look at the equation that sits at the heart of every attention layer in the transformer. Here it is, scaled dot product attention. In plain language, this equation does 4 things. Take each token's query, that is this Q, right? And it is asking, or it is saying what is it, what it is looking for. It is telling us what it is looking for. Compare it against every other token's key, right? This is key, K is key. What it tells us, what each token has to offer, right? So when we ask a query, we are seeing at this K and asking ourselves, okay, what this key has to offer me, how relevant this key is to me. Then we scale the score so they don't blow up and apply a softmax to get a proper weight, right? So that it is between 0 and 1. Then multiply this with a value, with values to get a weighted blend information. Here is how I like to think about it. Imagine you walk into a library with a question in mind, right? That is your query, your question. I need information about ancient Rome. Okay. Every book has a label, right? The label. Every book has a label. That is your key. It's the book. The label tells you what that book has to offer, what each token has to offer, what each key has to offer, right? That is the key. Ancient history, modern physics, Roman Empire, cooking, etc. You compare your question, right? You compare your question with every spine label to figure out which book are most relevant, right? Ancient history, Roman Empire seems to be more relevant. Then you open the relevant book and read its content. That is value. That is the value. You sort of extract the information, summarize it. The division by the square root that you see here, that is just making sure that librarian does not get overwhelmed when the labels are really long, when these labels becomes really long. It keeps the score in a sensible range so softmax can do its job. So to summarize, multiply queries by keys to get the relevant score, scale them down and apply softmax to get a weights that sums to 1 and then multiply with values. The result is that each position get a custom each position gets a sort of a custom mixture of information from all other positions weighted precisely by relevance. The best way to understand what the equation actually does is to watch token communicate. Okay. On the screen, you see the information routing in action. The bottom token is the query. It is asking what information do I have? I have information though. The top row tokens are the keys and values. Each respond with how relevant they are. If I move the slider, see the query change. Now it is cat. Watch how the attention pattern completely shift. When cat is the query, the connection sat and mat lights up. Those are the most relevant words. When you move to, let's say, sat, now you can see the pattern changes entirely. Each token send out a query, what information do I need? Every other token respond with its key. Here is what I have to offer. The dot product between query and key determines how much information flow among each connection. High relevance, the connection carry thick flows. Low relevance connection carry almost nothing. The result is that every token's output is a custom blend of all other tokens, weighted precisely by relevance. The transformer did not just achieve comparable result, it fundamentally changed how fast you could train these large models. Watch the difference, we have seen this before. On the left, the RNN process token one at a time, step 1, step 2, step 3, step 5, 5 steps for 5 tokens. On the right, the transformer does it all in one parallel step. All 5 tokens light up at once. This is not a small improvement, that is fundamental change in how you use hardware. And this gave 3 massive wins. First is training speed, order of magnitude faster, right? Because GPU cores actually run in parallel. Then scale. Faster training means you can use more data with bigger models. This is what unlocked the scaling revolution that led to modern large language models. And quality. On sort of major translation benchmarks, the transformer matched or exceeded the best recurrent model while using far less training time. Okay, the transformer brought enormous gains, but it came with one important trade-off, and we should be honest about that. Self-attention compares every token to every other token. For sequence of length n, that means n times n comparison, right? N into n. Double the sequence length, the cost quadruples. You have seen this graph before, right? Use the slide to increase the sequence length and watch how the comparison works, right? Like at 50, if we take 50, it's just 2,500. If we take to 500, it's 250,000, right? That is quite a jump up. For typical sentence of 50 and 100 tokens, this is no problem at all. But for a very large document of thousands of tokens, the memory and compute cost grows rapidly. And this quadratic scaling is exactly what drove an entire field of efficiency research. Sparse attention, linear attention, better memory handling, etc. etc. For now, just know that the vanilla transformer trades long sequence efficiency for parallelism and quality, and for most practical length, the trade-off is maybe massively worth it. Okay, let's make sure the core idea have landed here, right? I'm going to put around 4 questions on the screen. Try to answer each one in your head before I reveal the answer. Sort of pause and ponder. Why must potential information be added in transformer? Because self-attention treats its input as a set, not a sequence. Unlike recurrent models that process tokens in order, self-attention compute all pairwise relationship at once with no regards for order. Without positional encoding, the dog chased the cat and the cat chased the dog would look identical. Same word, same set, right? Positional encoding inject order information directly into the token representation, so the model can distinguish positions. What are the 3 sublayers in the decoder block? First, mask multi-head self-attention. The decoder attends to its own previous output with a mask preventing it from seeing future tokens. Second, encoder decoder attention. The decoder queries the encoder output to access the source information. Third, a position wise feed forward network applied independently at each position. Each sublayer is wrapped in a residual connection followed by a layer normalization. What does Q times K transpose represent? It computes a relevance score between every pair tokens, right? Pair of tokens. Each row of Q holds one token's question, and each column of K transpose hold another token label. The result is a matrix where entry I, J, tells you how relevant token J is to token I. This raw score gets scaled and passed through softmax to become proper attention weights. What was removed from prior architecture? Recurrence. No more processing tokens at tokens one at a time. Convolution. No more fixed window local patterns. What remained was attention as the sole computational mechanism paired with feed forward networks. This made the architecture fully parallelizable during training, and probably the reason why the paper also got called "You Only Need Attention." Let us bring it all together. The core proposal we had: replace recurrence and convolution entirely with attention. Process all positions in parallel. The design: 6 encoder layer and 6 decoder layers, each built from self-attention, feed-forward network and residual connections. The decoder adds masking and cross-attention as an extra layer. Positional encoding. No recurrence means no built-in sense of order. Sinusoidal encoding injects position information before attention runs. And the trade-off: massive parallelism and quality gains, but self-attention scales quadratically with sequence. For most practical tasks, this is sort of overwhelmingly positive. And that brings us to the next question. We have the architecture, we understand the attention equation, we know the blocks that fits together, but how does raw text, that is letter and words, actually become the vectors that feed into the machine? In the next episode, we'll cover tokenization and embeddings. You will learn why subword tokenization won, how embedding space start carrying meaning before attention even runs, and what happens in those first critical layers that convert human language into mathematical representation. If that sounds interesting, make sure you subscribe so you do not miss it. I will see you in the next one.